This is the internal combustion lab, and we are Group 3. We, the engineers of Rudell, have been tasked with determining the system parameters and control for Generative Energy Systems' newly built generator. This generator is based off a modular internal combustion engine, and in order to assist with analysis, the engine has been equipped with an encoder in order to detect both the engine and motor shaft positions, and a force transducer in order to detect the engine and motor torque. We will be collecting and analyzing data to specifically calibrate the force transducer to obtain a relationship between voltage and torque, determine the IC engine's mechanical properties, characterize the engine's full 4-stroke cycle, and model the engine's output with a simulated combustion in order to maximize the work output.
Shown in the figure of the slide is the experimental setup. In the setup, a force transducer is attached to a moment arm, which is connected to the motor. An encoder is attached to read the angular position of the motor. In experiment 1, the engine head was not attached to the engine, which allowed us to characterize the mechanical properties of the IC engine by measuring dimensions that will be used for calculations as seen in the table on the right, as well as deriving the work of friction, work of the motor, and the moment of inertia of the flywheel. In experiment 2, we attached the engine head on, but did not inject air into the system. This helped us to characterize the full 4-stroke engine and calculate work of the air in the engine. Lastly, in experiment 3, we will be injecting air into the system to simulate combustion. Data from this experiment will help us calculate the discrepancy between our theoretical and experimental models of the engine. For each experiment, a LabVIEW VI was used for data collection. The important variables that were collected were the encoder angle, force transducer voltage output, time, and 10-degree indices. The relationship between these variables helped us with future calculations.
Calibration is necessary to convert measured voltage into a meaningful force. To do this, known weights are added to the calibration arm, and the voltage is recorded for each set of weights. Multiplying the known weight of the masses by the measured calibration arm and acceleration due to gravity to get torque, and then taking the linear regression of the measured voltages versus the calculated torques gives the slope and intercept, which represent the gain and the offset voltage respectively. These are used to create the torque calibration equation. The equation shown is the work-energy balance equation for experiment 1. Using this equation, the work of friction and work of motor are calculated and used along with angular velocities at A and B to solve for I-fly. Work done by the motor is calculated using the sum of the areas under the average torque for each bin of 10-degree angular incrementing intervals for each data set. The work done by friction is the area under the curve for steady-state torque and time span that it takes to reach steady state. Angular velocity A is the initial angular velocity, while angular velocity B is the steady-state velocity. Steady-state angular velocity is calculated by taking the average change in angular position with respect to time for each 10-degree bin using data after the motor reaches steady state. These calculations are done for a system with 3 flywheel masses at low speed, medium speed, and high speed, as well as a test for 1 flywheel mass at medium speed. You'll see depicted the test for medium and high speed. Since there is no head on the motor for this experiment, there is no air pressure, therefore no work done by air. Work due to piston is negligible because there is a high flywheel inertia, and work discrepancy is assumed to be 0 for this case.
The 4-stroke cycle for the internal combustion engine can be seen by these 4 stages. First, during intake, the air comes in. Then during compression, that air is compressed. During ignition, the air kind of expands on the piston while it moves down, and in exhaust, the air is moved out while the piston moves up. So the compression and ignition strokes are the most important when dealing with the air and the work that's done, and that's because that's where the air is actually doing work on the piston itself. All of the work done by external and internal factors can be modeled by this equation, and we can neglect work of the piston and work discrepancy initially because those values are going to be small or negligible in consideration with the other values. Since we want to find work of air, let's talk about how we're going to find the other variables in order to find this value. So we can put the head on the internal combustion engine, but not inject any air yet, and this is going to help contain our air to see how much work is being done without having the external influence of other factors. We can run this engine at multiple different speeds, and I'm going to look at the low speed data and walk you through the process of how we actually found the work of air. So you can segment this data into the 4 different strokes that we just talked about, and we know that compression to ignition, that point is going to be when the torque of the engine is at its highest magnitude, so that kind of helps us with segmenting the data. Next, let's talk about how we find the other variables. Work of friction is going to be equal to torque of friction times delta theta. We have torque of friction from the first set of experiments, and that's going to be 1.056 Newton meters for this low speed setting. Delta theta can be found as the change in crankshaft angle for each of the different strokes, and you can see from point A to B, that's where we're going to talk about compression for now on this example. We find the work of the motor by finding the numerical integral during each of the strokes to see how much work the motor actually did during the whole system. And by solving that last equation, we can find the work of air, since we now have work of motor and work of friction. I-fly was found during the first week as well, and we have that value, and angular velocity for point A and point B can be found from some of the data that we read during the actual engine cycle. Let's take a look at some of the numbers that we have. If you look at the last column, you have work of air for each of the 4 different strokes. Intake and exhaust have very small values in magnitude compared to compression and ignition, and that's as expected, because like we mentioned, during compression and ignition, that's where you actually have the work done by the air on the system itself.
Formulas and assumptions, the uncertainty values for combined uncertainty of average torque, combined uncertainty of change in theta, and the combined uncertainty of work of motor are calculated. As you can see, for the work of motor calculated values, the uncertainty bounds are used when considering the exact values of these calculations. One must account for the uncertainty when comparing values to theoretical values. In experiment 3, there will be the addition of injected air into the system. This means that both the work done by air and work of discrepancy will need to be calculated. Work of air is calculated the same way as it is in experiment 2. The calculated work of air will be compared to the theoretical work of air based on volume and pressure measurements. Going forward, the work of discrepancy can be found as the difference between the theoretical work of air and the experimental work of air.
Conclusion. We found work air at each stroke in the cycle. Work air is important for compression and ignition cycles as the air is doing work directly on the piston, and the greatest magnitude values we had found were 16.96 joules in the ignition cycle and 13.62 joules in the compression cycle. Using the found work air values, we are going to find the discrepancy between the model and the experiment by modeling the engine output with the simulated combustion, by determining the crankshaft angles at which air is injected into the engine to maximize the work output. Thank you.